next up, we have Chiara, Ferrari, Wong. If you are here, feel free to, excellent, fantastic. So I will set the timer. We can see your slides okay.
Okay, great.
And I will start the timer whenever you're ready.
All right. Well, hello. Today I will be presenting Lunar HyTI, which is a thermal infrared hyperspectral imager concept for meter scale data collection from orbit. Lunar HyTI is a hyperspectral mapper that uses thermal infrared spectroscopy to detect silicate mineralogy, as well as the 6-micron emission feature to detect molecular water. It does so at 4-meter scale spatial resolution, which is 4 times that of any previous or planned orbital spectral remote sensing experiment. I'm going to start with this slide emphasizing the key takeaways of what I'll be talking about today and what Lunar HyTI would be able to achieve. In the science realm, Lunar HyTI would enable direct hyperspectral measurements of mineral compositions of individual lunar boulders, as well as characterize the mineralogy and water content of the deposits of small fresh craters with diameters as small as 10 meters. This capability would also work hand in hand with Artemis mission support, as it would be able to map the lunar South Pole and provide mineral compositions of every small crater and large boulder in the polar regions. So Lunar HyTI addresses 2 major scientific questions for the moon directly from the Planetary Science Decadal Survey. The first of which is, how do the structure and composition of each planetary body vary with respect to location, depth, and time? And the second is understanding the the composition and distribution of volatile chemical compounds. And so in addressing these questions, Lunar HyTI will provide maps of the mineral compositions of small fresh craters and boulders, as well as map the distribution of molecular water, like I said before, globally and at Artemis sites. So we'll dive a little bit deeper into some of the science measurements here. The first of which is hyperspectrally measuring mineral compositions of individual boulders and small fresh craters. The reason why we would want to look at boulders is because rocks exhibit less mixing than soils and are less space weathered than soils, since their lifetime on the surface is limited by impact and thermal breakdown. And while many highland rocks are mixtures themselves or breccias, if we were to look in settings like basin rings and central peaks, we might be able to find boulders of primary igneous lithologies. And with Lunar HyTI, we would be able to collect this data at 4-meter scale spatial resolution, which would thus increase the likelihood of finding a boulder of primary igneous lithology. In terms of these measurements and Artemis's science goals, HyTI will work on determining the extent and composition of the primary feldspathic crust through measuring the feldspar to mafic ratio of anorthites, determining the inventory relationship and ages of non-Mare rocks through determining lithologies present at the central peaks and at silicic volcanic constructs, and then also work towards the goal of determining the bulk composition of the mantle by seeking evidence of ultramafic rocks in basin rings and pyroclastic deposits. Our second major measurement would be to map the distribution of molecular water globally and at Artemis sites using that 6-micron emission feature, which is the same emission feature that Honeyball et al. 2021 detected using an airborne observatory. And this would be to understand the composition and distribution of volatile chemical compounds on the moon. So some additional goals and Artemis for Artemis support are that, along with mapping the 6-micron feature, Lunar HyTI would also be able to detect changes in the molecular water signature due to spacecraft traffic and surface operations. It would also be able to determine silicate mineralogy and water content of boulders and deposits of small craters, specifically to inform pre-mission EVA planning. It could search for exotic material deposited, maybe from the rays of Jackson and Tycho. And then additionally, it could map the distribution of micro cold traps within 10 degrees of the pole by measuring the temperature at high temporal and high spatial resolution, which would be 4-meter spatial resolution. Lunar HyTI itself, as a concept, is a maturation of HyTI, which is also known as the Hyperspectral Thermal Imager. It's currently being constructed under NASA's Earth Science Technology Office's INVEST program as a 6U CubeSat mission that's scheduled to fly in early 2022. HyTI as it currently exists does not meet lunar science requirements because it has a low frame rate detector system. It's been designed for low vibration launch and as well as been designed for low Earth orbit. So in terms of a lunar application, HyTI's technology readiness level is a 4. But now lunar HyTI is nearly identical to HyTI, but there are a few exceptions. So the first of which is that while lunar HyTI is going to use the same infrared detector array as HyTI, it will use a high-speed readout integrated circuit, or ROIC, in order to meet spatial sampling requirements. It will also have radiation-tolerant camera electronics. It will have to be ruggedized and tested to the general environmental verification standard for planetary launches. This thermal design will be upgraded for lunar orbit operation, and then it will use an athermal telescope, while terrestrial HyTI uses a focus mechanism on the telescope objective. Now, lunar HyTI is going to operate between 5.5 and 11.5 microns at 10.8 wave number resolution to map water, silicates, and other mineral emissions. From a 20-kilometer orbit, the diffraction limited spatial resolution is going to be 4 meters, and the swath width is going to be 1.4 kilometers. The signal to noise ratios vary from about 150 near 6 microns to over 1,000 past 9 microns for surface temperatures between 250 Kelvin and 300 Kelvin. And these signal to noise ratios meet or exceed the TESS and THEMIS signal to noise ratios that demonstrated successful mapping of silicate minerals on Mars using their features in the 7 to 14 micron region. Broadband thermal imaging using the instrument is also available and at 4 meter resolution, and the noise equivalent delta temperature is 1 Kelvin at a surface temperature of 50 Kelvin and about 1 millikelvin at a surface temperature of 300 Kelvin, which is sufficient to characterize any nighttime surface outside the PSRs. So I'm going to expand just briefly on the instrument spatial resolution. Lunar HyTI is able to achieve 4 meter spatial resolution with its current optical design. However, there is enough signal to achieve our science goals at 1 meter spatial resolution, but it would require a very large telescope and also an optical, and thus it would require an optical redesign. Regardless, the data products that Lunar HyTI would return would complement Lunar Trailblazer's wide field of view with very high resolution composition and temperature measurements in the thermal infrared. So finally, we wanted to conduct a general survey from the population here. I know everybody here really likes acronyms, but we were thinking about renaming this concept Rockstar instead of Lunar HyTI. So if you'd like to leave a comment in the chat saying which one you prefer, and if you hate acronyms, you might hate Rockstar. We never know. Or yeah, okay. Anyway, so here's the summary once more. In some new developments for this concept, we recently submitted a DALI proposal to conduct advanced development of this instrument for future lunar missions, and we plan to propose to the next Simplex call. Anyway, thank you very much. I can be reached for questions at that email or in the chat or in the question section. So thank you very much.
Brilliant, thanks very much. Maybe we could get a poll up together on Zoom during the discussion section, if you like.
That'd be great.
So yes, once again, please do write any questions in chat. And while people are typing, I guess I've just got a quick question really. When you sort of talk about wanting to map boulders and stuff, do you expect these boulders, sorry?
Oh, sorry.
Sorry, do you expect that the boulders to have quite fresh surfaces, or are they expected to have lots of sort of dust covering from nearby sort of cratering impacts and stuff like that? Do we know that, or is that a big unknown?
I think I'm not quite sure. I would expect them to be relatively fresh because they are less weathered and than say like soil. But yeah, I'm not actually 100% sure on the dust cover.
There's a lot of support for Rockstar in the chat, it seems. Okie doke. Well, yeah, if there are no other questions, I guess we'll thank Chiara once again and move on to the next talk.